For the remaining time that we have, I want to introduce you to the idea of work done by a force in the most basic kinds of examples. I was hoping to have time for more complicated examples today, but we don't. So let's keep it real basic today, and Friday we'll do more complicated examples. And I'm going to illustrate with my calculator here, okay? I could stand in front of you, but I'll do it. You can look at the screen if you want, if you prefer. Here I am, I'm holding my calculator. If I had scissors with me, I'd emphasize that I'm holding my scissors and I'm not running with scissors. Okay, holding my calculator steady. What am I doing? I am exerting, to keep it steady here, an upward force against gravity to counteract gravity. In fact, the force I am exerting straight upwards exactly counteracts gravity because it's sitting there still. How much force is that? It would be 9.8 times the mass. 9.8 meters per second squared times the mass, whatever it is in kilograms. Maybe it's a half a kilogram, I'm not sure. Probably not that much. Quarter of a kilogram. 9.8, maybe in the ballpark of 2 or 3 newtons is the final units. Meters per second squared times kilograms turns out to simplify to newtons units for force. If I move this calculator upwards a certain distance, and if, as I'm doing so, I'm traveling at a constant velocity upwards, I'm actually exerting the exact same force against gravity. But because I gave it an initial velocity and kept it constant, that force keeps it moving at a constant velocity. Technically, I have to exert a higher force than gravity to get it moving in the first place, and a lower force against gravity to slow it down to a stop. Sort of ignore that initial speeding up and ending slowing down, and just pretend, for sake of simplicity, that I move it at a constant speed the entire way. When I do that, the force that I'm applying is doing work, we say, against gravity. I am applying energy, you might say, to give this mass more potential energy because it's higher. And if it fell, it would do more damage to the table here when it's higher than when it's lower. Of course, not much damage to the table. The damage would be at the molecular level, I guess. Probably be more damage to the calculator itself. What is the work done by the force against gravity? It's defined to be the magnitude of the force, which I'm assuming is constant, times the distance traveled against gravity. Work done by force in this case, force is upward, gravity is downward. We could say it's a force against gravity. But you can also think about force, work done by a force, even when the force is not against gravity, like a horizontal push. If it's pushing something on a rug, the work is being done against the backward force of friction. Okay, so there's lots of different situations where you can think about this, but in the most simple kind of conceptual thing, and this is a constant force. Constant force is the magnitude of the force, I'll just call it the force itself, times the distance. Standard units, SI units, and it is important to think about units for this section, very important to think about units and make sure you get it right. Force was in newtons, and distances in meters. We could abbreviate this Newton meters in times m, if you like, Newton meters. However, this turns out to be equivalent to units of joules, which we can just abbreviate J. Same as units of energy. Does this really make sense? Turns out it does. I'm not going to fully explain it. But again, remember, effectively, when I apply a force to this thing to move it upward a certain distance, I'm doing work against gravity. Effectively, the amount of work that I do against gravity, whatever that might be, 0.25 newtons times half a meter, 0.125 joules. No, it's not necessarily 0.25 newtons. 0.25 kilograms times 9.8 meters per second, more like about 2.5 newtons times half a meter. In the ballpark, where am I in my mental math? Around 1.25 joules or something like that. Somewhere in that ballpark, 1 to 2 joules. I forgot exactly where it was in my mental math. And that is the amount of extra potential energy that this has when it's up higher than it was to start with. Potential energy for the purposes of dropping it and causing damage, say. So it is definitely related, intimately related to energy. In non-standard units, you know, I guess you call them British units, excuse me, British units, but, you know, British people don't use British units anymore. Only Americans do. And what else is it? Maybe Singapore does or something. That might be wrong. I don't know. Units of force are actually pounds, and units of distance are feet. And you'd write your units as foot-pounds, typically. Maybe abbreviate FT times LBS, foot-pounds. Does that have a shorter name? I don't think it does. If it does, I'm not familiar with it. Foot-pounds are also units of energy. Why bring this up? Because it comes up in some of the homework problems to do it this way. Silly. Okay. Oh, I don't care that much, to tell you the truth, but yeah, you should be educated about it. Pounds are units of force in British units, which again, only Americans use. In other words, weight is a force. Okay, I'll go ahead and say my weight. I'm about 175 pounds. That's my weight near the surface of the earth. If I go way up miles into the sky, my weight is actually smaller, because the gravitational force that's acting on me is smaller because I'm further from the center of the earth. If I'm in outer space, you know, I'm weightless. A little bit of a lie to say it's completely weightless, but if you're way out in outer space, you are effectively weightless. You have no weight. You're not in a gravitational field. You do have mass, though. You still resist acceleration. You still have to apply a force to accelerate a rocket, even in interstellar space. You still have mass. Kilograms in SI units. Anybody know the units of mass in British units? Slugs. Okay, we're out of time, but give me one more minute. Kinds of problems I'm going to assign are going to be real basic. Like this basic, 1, 2, and 3. You just need to multiply force times distance and get the right units, which could be inch pounds, for example, number 1. And I'm also going to apply, assign maybe a couple of these problems about springs. And with a spring, the force is actually not constant. When you compress a spring, you have to push harder and harder to keep compressing it. It's a linear function of the displacement of the amount of compression. X is the amount of compression. And in that situation, it's still fairly easy. You got to integrate the force function. Intuitively, you think about chopping up the motion into small distances of length delta x, and over a small distance, the force is effectively constant. And then you add up those small amount of works, and in the limit as delta x goes to 0, you get an integral. So this is still a calculus situation. Make sure you do the reading about the other harder kinds of problems related to like lifting chains up toward roofs and also pumping water out of a pool. Those are harder problems where we definitely need calculus. We'll talk about those on Friday, but read about it before Friday. Okay? See you then.